You see her on the screen. I'm going to stop sharing now. And I'll just say a few words. Microsoft is working on the most complicated kind of qubits, the topological qubits. They have languages and architectures and Q-sharp and a lot of materials. There was going to be a workshop tonight, and Mariia, as well as Mark and Chris Granade, were going to run it. A lot of non-essential travel has been canceled, almost all over the place. So they can't be here tonight. Okay, our own presenter, Sarah Kaiser, was going to talk to us about a book that she's writing with Chris Granade, but she doesn't have a voice anymore. And extremely grateful to Mariia for agreeing on last minute to present. There she is, always wonderful, always knowledgeable, Mariia Mykhailova.
Thank you for such a nice introduction. This is indeed one of the shortest notice talks I've ever given, but the shortest notice was about 15 minutes, so you're good. Can you both hear me and see my screen?
Yeah, I think I have.
Excellent.
Okay, perfect.
This is always helpful.
Mm-hmm.
So, you are going to hear a talk from Sarah about her work with Chris on the book which would tell you how to learn quantum computing using Python and C#. I think this slide is all I know about this book, and this is not the talk you're going to get. Instead, I'm going to tell you about our experience teaching quantum computing using C#. So I will not go too deep into the description of C# as a language itself. Rather, you will see bits and pieces of it now and then as I talk about what exactly we did with it in our work teaching people quantum computing. So I think for this event, I don't need to spend time persuading you that quantum computing is promising and exciting, and there is a lot of interest in people learning it, and correspondingly in us helping people learn it.
Right.
So last winter, a bit over a year ago, we had an exciting opportunity to teach a class on quantum computing at University of Washington. So most of the talk I will be talking about that experience. When we had this opportunity, we of course had to think and figure out how we wanted to teach quantum computing. We looked at the existing materials and courses, and a lot of them, not all of them, but a lot of them, shared some similar features. First of all, quantum computing is considered to be a complicated topic, which it sort of is. So most of the offerings targeted people who had a lot of mathematical and sometimes physical background, and very frequently graduate students. Our class was geared towards undergraduate students, and we wanted to make it available for younger students with less mathematical background. The second thing we observed was that a lot of courses taught quantum computing in the context of physics. So they started by presenting physical implementation of qubits and superposition, and then proceeded to think about computing. But really, quantum computing has grown so far over the past several decades, that it has a lot of topics in it, and putting all of it in one course becomes less and less practical. At the same time, parts of it, the parts which deal with physical implementation of the quantum devices, are really heavy on physics, but higher level parts which deal with quantum computing, quantum algorithms and applications are not really hardware dependent. They can be taught completely abstractly in terms of math. And this is the choice we made. We wanted to not have any physics in our course. Finally, a lot of courses focus on, come on, theoretical presentation of the material without any practical hands-on component. So you will often see that everything taught is taught as a lecture, and the exercises are written assignments and exams. So the algorithms don't really get implemented. I talked to one student recently who had a course on quantum computing and actually computing algorithms and applications, but all the implementations of the algorithms they did in class were on paper. I don't think it's very practical if you want to grow somebody who is a quantum software engineer. Uh, if you think about it, if you train classical software engineers, would you want to hire a software engineer who spent half of their time learning transistor physics and half time learning complexity theory, and they only ever implemented algorithms and wrote code on paper? You probably wouldn't want to hire them. So these three things defined our approach for our course. So first, we wanted to teach quantum computing through programming. We really wanted the students to get more hands-on practical experience with implementing algorithms. For many algorithms, this is the only way you can really start to understand them. My favorite example about this is Grover search algorithm. The first time I implemented it, as I just learned it, I figured out that, well, it has iterations. And in classical computing, usually the more iterations you do, the better. So certainly it must be the same here, right? It turned out that it's not quite the same with Grover's search. And this is something that a lot of books just don't focus on. They say, here is the circuit, you do it a number of iterations, you're good. So I learned this lesson, not particularly hard way, but it was only when I actually implemented this algorithm was that I actually realized this is what you mean by the optimal number of iterations. So this is what we did. We tried to avoid proofs which require a lot of mathematical background, especially in the more advanced topics. And our students didn't have a lot of math background. And we also eliminated a lot of physics. We offered a lecture in the end of the class. Like one of the last lectures we spent on the physical implementations of the quantum devices. But during the course, we just talked about qubits and qubit states and algorithms in mathematical terms. Some data on the course. So it was led by our general manager, Dr. Krista Swori. I was the programming guru. It was actually officially in the slides like this. So I was responsible for all the C# components of the course. Okay, I'm sorry, the slides just keep running ahead. And multiple researchers on our team helped us to prepare written assignments and to give 1 or 2 lectures on their domain of expertise. So it was really a team effort. The course was hosted in the Computer Science and Engineering department, which is unusual for quantum computing courses, a lot of them are hosted in physics departments. We targeted third and fourth year undergraduate students. We actually got one student who was as early in his studies as the first year, and he did pretty well in our course. So I would say it was good. Our students were a mix of physics students and computer science students, and some of them had math background. So I think we had around equal number of all of them. The course duration was 10 weeks. We had 2 lectures per week, 90 minutes each. Krista hosted office hours, and I was kind of always available online for the students. We did not have an official lab section, which was not optimal, and I will talk more about it later. So when we announced this course, it was extremely popular in the university among the students. We started with 50 students signed up and a full wait list. As the course went on, naturally some of them dropped off, so we stabilized at around 35 students. Here is the structure of the course that we had and the grading that we did on the course. We had lectures during which we offered students the theory and the basic concepts and algorithm descriptions. To keep this, well, to grade this part of the course, we offered them written assignments. We had bi-weekly written assignments. I will talk more about them later. And you see that the main part of the grade, 80%, was about the practical implementation of algorithms. We had programming assignments and the final project instead of the final exam. In our lectures, we covered a typical list of topics which you will find in any introduction to quantum computing course. In fact, we covered more than we should. It was just a 10-week course, and it was targeted at undergraduate students. And by the end of the course, a lot of students just kind of lost track of what's going on, especially when we started talking about quantum simulation, quantum chemistry. Those are complicated topics, and it was interesting as an overview, but the students ended up not getting deep into it, except a couple who did really well. So for our future courses, we are going to cut the most complicated topics so that we can spend more time on the fundamentals and make sure that the students get really comfortable with them. So for written assignments, we offered one written assignment per 2 weeks, so it covered multiple lectures. And they were theoretical tasks, like here you can see one example of them do some manipulation with a circuit. They didn't involve any programming and they were graded by hand, so very, very standard. We found that our written assignments were too complicated for a computer science undergraduate student, especially once we got to chemistry. In the next courses, we would either drop written assignments completely or pick a simpler subset of tasks that better suits their level. Now, this is all that we did that was standard, and now we get into the interesting parts, the actual programming hands-on parts of the course. All of our programming tasks and materials were done using Microsoft Quantum Development Kit, which is something that my team was working on. That includes a kind of package of tools and libraries that you need to develop quantum software. So it has Q#. It's a domain-specific language for expressing quantum algorithms. You will see bits of it later today. So the neat thing about it is that it allows you to write code both in kind of low-level terms, in terms of quantum gates. So if you have a circuit, you can translate it to Q#. Exactly. And at the other hand, it can allow you to write code in very high-level terms. So if you want to express a sophisticated algorithm, you don't need to break it down into a circuit before expressing it. You can just write it like you would write high-level language in a classical language. Then the QDK has integration with Visual Studio and Visual Studio Code. I will also show it to you a bit later today. And the neat thing it got about a year ago was Jupyter Notebooks. It was not in time for our first course, but we're using it in our next things. Then to enable the students to actually run the code that they have written, which is sort of important if you want your course to be hands-on. QDK has simulators, so which you can run on your computer. So full state simulator, TOEFL simulator, and a resource estimation, which allows you to figure out how big a quantum device you would need to run your program and how long it's going to take, even if you cannot actually run it in simulation on your computer. Then it has libraries which have both common common patterns which are kind of smaller than whole algorithms. For example, amplitude amplification, phase estimation, building blocks which you can use as parts of larger algorithms. And it has also specialized high-level libraries such as quantum chemistry and just released last month's quantum machine learning library. And finally, it has a set of tutorials. We call them the quantum katas, which is what I'm going to talk about next. So the quantum katas are my pet project. I basically came up with this idea and I'm the primary maintainer of this project. They are collections of programming exercises and programming tutorials that help people learn quantum computing and learn Q# at the same time. This is an open source project that is free to use to anybody. You can see a very useful link on the bottom of the screen, and actually let's be adventurous and let me show you a demo of the katas. That's more interesting than talking to the slides, right? And you have to tell me if at any point you lose my screen. I think I'm sharing the screen and not the slides, but just to be on the safe side.
So we see a list of tutorials.
Excellent.
Can you make the text bigger?
In the browser. In the
browser?
yeah.
Okay.
One more step?
One more.
Thank you.
Yeah, let's keep it like this, otherwise it gets more, we don't get a lot of vertical space. So this is the Jupyter version of our katas. I'm running it on my laptop. You can also run it online if you don't want to install QDK. So here is the list of the katas. You can see there are quite a lot of them on different topics. And let's take a look at one of the first katas, superposition, so that you can see what a kata is. And a kata is a sequence of exercises that cover one topic in quantum computing. Here, of course, since it's superposition kata, it covers the first concept that people learn in quantum computing, the concept of superposition. And it covers this concept by offering series of exercises. Each exercise is a well-defined task which describes you what you are given and what you need to do and what you need to return. In this case, the first task is preparing a plus state. So you are given a qubit and you're guaranteed that this qubit is in zero state. You need to change the state of the qubit to a plus state, which, as we probably all know, is superposition of 0 and 1 states in equal measure. Anybody wants to tell me how to solve this task?
With a Hadamard gate?
Yes, exactly. Okay, I'm not sure what's going on here. Sorry, I will have to restart it. It looks like I'm on the old version here. Sorry about that.
No problem.
Basically, the version that this notebook uses is newer than the version I have installed on this laptop. And since I want to do a live demo, it has to run, so the versions have to match. Yeah, so as you pointed out exactly correctly, we need to apply Hadamard gate. And here in this code cell, we have a snippet of C# code, which gives us a signature of an operation that we need to implement. And okay, it's better now. So we can write any code that we need inside this operation. And this special string tells us that the backend needs to run this test once the solution is executed. It might... okay. Live demo did not exactly succeed. Let me show it to you in the Visual Studio version, which should be less sensitive to these things. So you can see that in Visual Studio it's exactly the same thing, but it looks less pretty. So instead of the version in Notebook, which has actual formulas and bold font and other nice things, in Visual Studio it all uses Unicode to express the formulas. Okay, if this version of live demo is going to... oh, I'm being silly. I can use the online version, which I definitely know that it works. I tried to avoid it, but my local installation is just not that nice. Okay, so basically, what I'm trying to do here, I'm trying to execute the solutions that I have just implemented for you. And each kata comes with a backend which, once it gets a solution, it runs the test that corresponds to it, and it validates whether your solution is correct or not. And it actually gives you this information back once you solve it. This is very important for learning because, well, it's one of the main principles of the good learning, you have to be able to get feedback on your work. Otherwise, if you are going through a book, for example, and the book has exercises, and you're trying to solve those exercises, you write them on paper, you don't know whether they're correct or not. And if you don't have access to a quantum computing expert to answer your question, you're not going to know if you have an error. So here I finally got this task to execute. And you see that the testing harness prints you what was the state that you wanted to prepare, what was the state that you actually prepared. And it tells you that your solution is correct. Now, if we go on to the next task, it's a little bit more complicated. You need to prepare a minus state. And if I'm being lazy and don't type anything in here, you see that the testing harness is going to tell me, this is the state you were going to prepare, and this is the state you actually prepared. They're different. So try again. Now, let's say I'm hopeless and it's the first time I see this kata. It's not bad, let's pretend. And I have no idea what to do here at all. This kata comes with a workbook. Workbook is a collection of worked out solutions for the tasks. So if I get stuck, I can go to this workbook and it will explain to me that here is what we learned in the previous task, and here is what we need to do in this task. Here is how it's similar, and here is what we need to do. So basically, it walks you through all the steps of the solution. We do not have such workbooks for all of the tasks, but it's a work in progress. Okay, so we looked at the first tasks. So far we have immediate feedback, and we have learning by doing, because people don't just see somebody doing the tasks for them, they have to try and do the tasks themselves. Now, as we progress through this kata, the tasks become more and more complicated. So in this task, for example, you need to figure out which rotation gate you need to use. Rotation gates are more complicated than Hadamard's and poly gates. Then you go to multi-qubit states. Then you go to multi-qubit states that are not separable. So you need to use some form of controlled gates, which is again the next step in the difficulty. Then you go to using classical input, the index you're given, to affect what you are doing to your qubits. So that's another concept added. Then you go to using unknown number of qubits. So you need to start learning how to manipulate qubit arrays and loops. And so on and so on. The tasks get more and more interesting. And in the end, the last task is actually one of my favorite tasks. It asks you to prepare a W state on an arbitrary number of qubits. And in this task, you need to use pretty much everything you have learned in the kata, because one of the solutions is to use arbitrary rotations and controlled gates. And you have to use recursion also to make your code neat. And the other one is to use post-selection. Prepare a larger state and then measure part of the qubits so that the rest of the qubits are in the state that you want. It's a very neat task. And basically, if the student goes through the tasks of the kata, they can kind of, without noticing it themselves, learn quite a lot and start to getting quite comfortable with the Q-sharp code. Okay. So this is what the front end of the kata looks like. And this the project I was showing you in the Visual Studio. I should probably increase letters here as well. It's kind of the back end of the kata. So it has a text version of the tasks. Then it has reference implementations. So this, for example, is the reference implementation of this last task that I was telling you about. So you can see that it has a fair number of control structures, qubit allocation, which is another helpful technique that you will learn in the middle of this kata. It has repeat until success loop, and it has recursion. So this is another help for students if the katas don't have the workbook yet. And the last important component is the test harness. Here is what it looks like. It heavily relies on C# libraries, in particularly assert equal and zero state, check, which basically uses other libraries to implement the check. For superposition kata, how we do the checking is we run the student's solution, and then we run a joint of the correct solution. So we should return to the zero state if their solution is correct. So you see that we check the solution based not on what sequence of gates it does, but on what effect it has on the quantum state. This is very important. For example, the minus state, you can prepare using multiple ways. And we want to be able to judge all of those ways as correct, regardless of which solution the student chose to do. This is one of the very first katas the students see. And as basically as the topics progress, so do the katas. You will see that we have stuff for the basic concepts, for simple algorithms. We have really good material for Grover's algorithm. Actually, this one is one of my favorite katas. It shows and teaches the student how to do the end-to-end solution of a problem using Grover's algorithm. So it picks a kind of problems which are easy to code, set problems. They map into quantum oracles really easily. So first of all, this kata teaches you to build the oracle. It teaches you how to build the AND operation, how to build the OR operation, the XOR for good measure. Then it teaches you how to combine multiple components into a larger function. So here you need to allocate extra qubits and use them to store intermediate result of computation before you continue. And you have to also learn uncomputing stuff at this point. Then it teaches you to evaluate one clause of a set formula. Here you need to manipulate the input you are given to figure out on which exactly qubits you need to do your controlled knot and what kind of controls they should be, positive or negative. And then finally it brings you all the way to implementing the oracle for the whole problem. Then it takes a detour to check that you have actually learned your stuff and implements the oracles for exactly one set problem that's similar but different enough for it to be interesting. And then the third part actually shows you how to use Grover's algorithm on this problem. So there is another kata which teaches you Grover's algorithm step by step. So here you just run the whole algorithm, and here you are supposed to learn that it should be robust to failures, like if you did incorrect number of iterations. And it should be robust to you not knowing how many iterations of Grover search you need to do. So it teaches you a fair number of useful skills. We also have some neat tutorials, which I probably shouldn't show you right now. I'll show you one very quickly, okay? I'll try not to run over the time too much. So a tutorial takes the idea of the kata and brings it to the next level. The kata is just a sequence of exercises. And a tutorial combines giving you the theory with the exercises to immediately internalize it. Like some books do, which give you the theory and then give you a little written exercise. So this is the same thing, except the exercises are programming. So here, for example, you get an explanation of what a subproblem is, and your exercise is how to convert the programmatic description of the formula into an actual formula. Then it goes through the classical algorithm of solving this problem and asks you to implement it. And then you go through quantum implementation. You learn to verify that the output is the actual output. And at each stage, for example, here, you see that a lot of code is already filled in. We realize that if the student is just starting, they might be not comfortable writing a lot of C# code immediately. So we teach the student to fill in the missing pieces of code, and those missing pieces of code teach them a lot about C# and about implementing the algorithm itself. And you see there are very detailed instructions on how exactly to fill those missing pieces of code. And once the students have done through all these pieces of implementing the solution exactly in C#, there is a companion Python notebook which uses that C# code and runs it from Python, because this allows to do some visualizations of the results. C# is not very good at visualizing things on its own. It needs basically a classical driver to run C# code and do the visualization. And this is what this notebook is doing. It's calling C# code here. Basically, it simulates a certain C# operation. And then it builds graphics based on this. So here it digs into the periodic nature of Grover search success probability. Okay, this was probably more than you wanted to know about the quantum katas. You can tell that they are my project.
Actually, I have a question. Have you run into a book called Little Lisper or Little Schemer by Dan Friedman and Matthias Verleisen ever?
No.
Okay, so the idea is that that was a type of programmed instruction of the kind you are promoting here, except of course yours is more dynamic. Is it true that you didn't have a lab because you would expect students to go through these katas, understand on their own, and then the truth would come out when they write their assignments and their competitions? Is that true?
So we didn't have a lab because basically we were not entirely free in choosing the structure of our course. So kind of in retrospect, we should have allocated part of the lecture time to lab time. But this was our idea of the next best thing we can offer to students. Because this was what we offered them to do instead of labs.
But it's engaging and they can do it on their own terms, at their own pace, and whether they do it or not is irrelevant, as long as they can write for their assignments and get good grades, as long as they can pass their exams, as long as they ask you questions if they don't understand something. So, very interesting.
Yeah, and there are other similar projects. I don't know the exact book that you asked about, but kind of the immediate push that I got to start actually sitting down and writing those katas was a project called F# koans. They are, well, obviously in F#, and they aim to teach pieces of F# syntax by also missing some pieces of code and asking the person to fill them in. They have different testing harnesses. They can provide more detailed feedback on where exactly the error is, but they're classical.
Yeah, I see. I'll send you a copy of that book. I have a PDF, and then you'll see what I. It's a very old book. It was really revolutionary at the time it came out, and it is fun. You start reading it, and you forget that you're learning. It teaches programming and recursion, and you forget because it just motivates you. But anyway.
Yes, that's the kind of effect I'm trying to achieve. This is supposed to be interesting, and kind of the student gets what's the word?
Engaging.
Positive reinforcement. Once they solve one little task, they start to feel better about this.
That's right. They own it. Yeah.
Okay. Now back, come on. Back to the slides. Now, as you correctly pointed out, to check that the students are actually mastering the programming skills, we gave them programming assignments. We gave them about one per week. Some of them ran longer because they were larger. And the neat part was that they were very similar to the katas. Basically, the students would get a file with task descriptions and the operation signatures they needed to fill. They would fill in the code and return it to the teaching assistant for grading. And they were automatically graded. Let me tell you, our teaching assistants adored me for it. Because anybody who ever taught a course knows that grading the tasks is a lot of work. And if we grade the tasks automatically, it leaves the person who does the grading to do kind of smarter engagement with the students. So instead of spending an hour grading those 15 tasks by hand, they can spend 2 minutes getting the grade, and then they can spend the other time engaging with the student and helping them understand the pieces that they missed.
That's right.
So automating technical work, I think, is very important. Actually, I'm teaching a course on quantum computing myself now at Northeastern University, Seattle, and I don't have a teaching assistant. And I just started to appreciate those automatic graders over and over again. Because this way I can spend very little time on the actual grading, and I can spend time actually explaining to the student where they were wrong.
Right, to customize the instruction.
So based on the students' feedback we got after the course, the students really preferred programming assignments to written ones. One thing we could have improved if it was possible for us to share the grading harnesses for the assignments with the students. We couldn't do it at that point because our reference implementations, as you have seen in the katas, were just plain text in the project. You cannot really share plain text answers to graded tasks. It defeats the purpose. But it would be very helpful because it takes some effort to verify that your solution is correct. And we could have saved this effort to the students. For the last programming assignment, we did something different. We offered the students the programming competition. We hosted a programming competition open to the public in the last months of the course. And we thought that it's a great opportunity to give our students something interesting and unusual. If you know some of the classical courses on classical algorithms or machine learning, sometimes offer the students to participate in competitions on Kaggle or Codeforces or other competition platforms. And I always thought that it's very interesting. So the contest had very similar structure to the katas. It was also tiny, well-defined tasks that you need to fill in the code. It had harder problems. They relied more on the math than the programming assignments did. And the contest site allowed us to provide the students immediate feedback. So they would submit their code and they would immediately know whether it's correct or not. And they could resubmit as many times as they wanted. Still, they didn't appreciate this luxury. Basically, the students found that it was too stressful and too hard. So it was shorter than other assignments. It had harder problems, and probably just the fact that it was a competition with a leaderboard was just extra stress for some people. Even so, we didn't take the place that they would take into account. We scored them based on the number of problems they would solve. And for the second part of the course, for about the last month, we stopped giving the students the assignments and both written and programming. and the students worked on their final projects. Basically, we tried to emulate life of a quantum computing researcher, software developer in those projects. The students would select and define a problem they wanted to work on. They would figure out how to solve it, first mathematically, then they would implement a sharp solution for it. Then they would evaluate this solution. For example, they would find the small test case which they can run on their laptops completely, because for example, one of the students did graph coloring problem using Robert search, and if you need to use qubits to describe your graph, you need a very small instance of the graph. So this gives you limitations, and the students had to explore those limitations and sometimes optimize their solution so that they would be able to run it on some interest test case. On the other hand, they would use other simulators like resource estimator or TOEFL simulator to either run special problems like quantum arithmetic, for example, on a different kind of simulator that gives you less flexibility but allows you to simulate more qubits. Or they would use resource estimator to figure out how big their solution was for a larger instance. They would write up their findings in a small paper, and finally they would present their work in an in-class talk. So we spent the last 2 lectures going through the students' talks. This was one of the favorite parts of the course for the students. The katas and the final projects were 2 most favorite parts, because on one hand it allowed to jump into the area that excited them and to learn something more, and on the other hand it was like doing something end to end, not just pieces. So what we learned from this course: first, the students really liked the hands-on approach for it, that it was not just mathematical but implementation based. The students found the class very challenging. At times they just said there's no way we can finish all the assignments in time, but very, very stimulating and inspiring. Some of them said that this class was the most inspiring class they've ever had in all their studies. Some of the things that really need to be done is having linear algebra and programming as prerequisites, or spend the first lecture reviewing the prerequisite material with care, because our students had quite diverse backgrounds and not all of them were familiar with linear algebra or even with programming before. One thing we did for this was we created a couple of tutorials, well, actually a set of tutorials here, which allow the student to catch up on exactly the pieces of complex arithmetic and linear algebra that are necessary for working with quantum computing. Because you don't need the whole linear algebra, you just need a very small subset of it, and you can catch up with it really quickly. So we made tutorials on this and on the basic concepts to help students be more thorough in their learning of this topic. Then it's really important to be able to have lab time for learning programming. Quantum katas are great, but still sometimes there are things there that the person can just get stuck, and it's important for them to be able to get unstuck. I was always online for the students to answer their questions, which was very helpful. And actually our students self-organized. They spend some time together working through the problems of the quantum katas. And that is another neat use of the quantum katas. They help people to structure their learning, and kind of students who went better could figure out things faster. were able to help the students who were falling a little behind.
So a quick question now is, this is a lot of work. It's also very well done. Do you anticipate, since it's supposed to teach Q sharp at the same time it teaches concepts, do you anticipate any changes in the katas as Q sharp might change? Might it become a little bit obsolete, any parts of your notebooks, or you think it's going to be fine?
Oh, I always update the notebooks as the key sharp gets updated.
Uh-huh.
So basically, the katas are always either on the latest version of key sharp or maybe lagging a month or two behind.
But
But
you have to be there and update them all the time, right? Just to keep them up to date.
yes,
Yeah, that's a lot of work too,
well,
but that's good.
yes, so it's a living project. I keep working on it, well, whenever I have time, which is unfortunately less than I would like to these days. But I'm very careful about updating it and creating new materials based on what we have seen, what are the topics which people get stuck at. For example, those first tutorials on linear algebra and on the basic concepts. We came up with them because we looked at how students work with the katas, and we realized that, okay, these and these are pieces that are very hard for them to grasp. So we create a new tutorial for that.
I see. Yeah. Sure. A question. We have a question.
Now, in the future, I know that Q sharp is new, and
Sorry, I cannot hear you
Okay.
very well.
Hang on.
Is there a,
So you're gonna get a second book.
oh, thank you. Okay, thank you. In the future, like in data analysis, data science field seems to grow quickly, and there are certain languages like Python, R. So how do you compare your Q sharp? In the future, are you going to add libraries that will deal with analyzing data, big data?
so we are working on adding more libraries to C#. One example is one machine learning algorithm that made it into a library and released about a month ago. But on the other hand, I'm not sure quantum computers are that good for analyzing big data. I have to tell you that I'm not a machine learning expert, so anything I tell you about quantum machine learning, you should take with a grain of salt. But to the best of my understanding, quantum computers are good for big compute, not big data. So basically
Okay.
something that has little data on input, little data on output, and this big compute in the middle.
Okay, so then, like home computers, probably we're not going to
Well, no,
focus on like basic applications then in
Currently,
quantum?
data loading is a problem, but in the future, hopefully, that's not going to be an issue. I mean, of course, you want a lot of data and then search through it or whatever, but at this point, that's hard. So the idea here was it's a different kind of computation. We're not used to it. Just like in the case of dequantization and machine learning, people have been trying to find quantum algorithms. They couldn't, but because they've been thinking in these terms, they end up with completely surprising and very performing classical versions that they wouldn't have thought about if they hadn't tried to find a quantum version. And that's called dequantization. So at this point, lots of data, not possible. It's called the data loading problem. And then the focus is on how the things actually compute. In the future, absolutely, but I'm not sure.
Okay, thank you.
Okay.
Okay, so we are nearing the end. Couple more minutes and it will be over, I promise. So for the outcomes of our course, first of all, I was very excited to see that several of the students' teams chose to frame their final projects as quantum katas on the topics that were not covered previously. And they actually contributed their work back to the project. If we take a look at the list of tutorials, solving graph coloring problems using Grover's algorithm is one of the students' project. The whole section of entanglement games are also done by the student. I think BB84 protocol and ripple carry adder also done by a student. And it is very, well, I think it's a very strong result that the students went in the course without knowing anything about the quantum computing. And they emerge from it 3 months later, not just being able to implement an algorithm end to end, but being able to express what they have learned in a way that can help the future generations of students. Admittedly, I helped them a little to polish their katas, to bring it up to my, incredibly high standards. But the bones were done by them. Then 4 of our students got internships in companies that do quantum computing. This is actually a very strong indication that we're doing something right, because typically quantum computing internships are for graduate level students who pursue their PhDs in quantum computing. And here our undergraduate students got them. 3 of them joined our team for last summer, and 1 of them Pacific Northwest National Labs. And actually 1 of the 3 students who were our intern last summer graduated and joined our team about 2 months ago. So that's very exciting also. And finally, well, we still have our curriculum materials. They are really nice and really reusable. The Northeastern University course I'm teaching now, I'm basically taking our first version of materials as the base and going through them and updating them, tweaking them a little. There was 1 lecture that I added and several that I'm going to drop, updating programming assignments, that kind of things. And we are very happy to share those materials with other universities, because we believe that quantum programming should be taught in a practical way. These are some of the universities that are already using our materials wholly or partially. And there are some of them who use quantum katas without using our kind of secret materials. So that's also great to see. So if you want to, learn more about our work or get access to our curriculum materials, please feel free to contact me. Come on. This here is my email, and here are some helpful links to the quantum katas themselves. And we actually wrote a paper about our University of Washington course experience that we were going to present later at SIGCSE, but since we're not going there, it's going to be a video. If you were going to go to that session, you do not need to go there now, because you have already learned everything I was going to talk about. So here is the link that you can get the whole paper and read it. Thank you.
Okay, well, thank you so much. And we're gonna take a 5-minute break and then get to the final keynote of the day. Once again, thank you for joining us, and we're gonna go into a break now. 5 minutes. Thank you.